Welcome to the tutorial for the homework 4. There are 7 big questions. Now let's look at the first question. There are 4 small questions, and we should look at the title. The title is Consider the Cyclic Quark question. Consider the cyclic problem restricted to graphs in which every vertex has degree at most 3. Call this problem cyclic by 3. The first question is to prove that the cyclic by 3 is in NP. Okay, the answer is to show that cyclic by 3 is in NP. We need to show that the cyclic by 3 has a polynomial time verification algorithm. The following algorithm V is such an algorithm, which runs in O V plus over 2 and multiple E. And the algorithm is like this. Look at it. On input G equals to VE K V plus such that the dV is larger than 3 for all V equals to bigger V, and valid if true, and if big V plus smaller than K, then the valid is false. And then for V in big V plus, do like this. If V don't belong to big V, then the valid value is false. For every pair of the distinct vertices UV in V plus, do like this. If UV don't belong to E, then valid value is false. And finally, we term the valid. Okay. Next question is the question B. What's wrong with the following proof of NP completeness for cyclic by 3? We know that the cyclic problem in general graphs is NP complete, so it is enough to present a reduction from cyclic by 3 to cyclic. Given a graph G with converse of degree larger than 3 and a parameter graph G, the reduction leaves the graph and the parameter unchanged. Clearly, the output of the reduction is a possible input for the cyclic problem. Furthermore, the answer to both problems is identical. This proves that the correctness of the reduction and therefore the NP completeness of cyclic by 3. Why the statement is wrong? The answer is polynomial reduction from cyclic by 3 to cyclic only shows that cyclic by 3 is not harder than cyclic. That is, if cyclic by 3 is NP hard, cyclic is NP hard. Exactly. It doesn't infer that if the cyclic by 3 like cyclic is NP hard, therefore it's not valid proof for NP completeness for cyclic by 3. And the third question is, it is true that the vertex cover problem remains NP complete even when restricted to graphs in which every vertex has degree at most 3. Call this problem phi3 by 3. What is wrong when the following proof of NP completed for cyclic by 3? We present a reduction from MVC by 3 to cyclic by 3. Given a graph G equals to VE with not degree bounded by 3 and parameter B, we create an instance of cyclic by 3 by leaving the graph unchanged and switch the parameter to lemma V minus B. Now, a subset C belongs to V is a vertex cover in G if and only if the complementary set V minus C is clicked in G. Therefore, G has a vertex cover of size larger than B, if and only if it has a Selig size of larger than E or equals to the number of V minus B. This proves that the characteristics of the reduction and consequently the NP compatibility of select by 3. And well, the answer for this question is that it is not true in all cases that a subset C belongs to V is a vertex cover in G, if and only if the complementary set V minus C is a clique in G. Consider the following graph G. Subset AB is a vertex cover, but the complementary set CD is not a clique. Therefore, the proof cannot be established. The first question is describe an O the number of V over 4 algorithm for select by 3. The answer is that let K be the size of subset we want to verify. Since the largest clique size is 4, if K is smaller than 5, ignore it, and for K larger than 4, check if every pair in the subset has an edge O K squared. If every pair has an edge, add it to the solution. We perform this process on all the subsets in the entire graph O the number of V over 4. Thus, the runtime complexity is O the number of V squared by over 4 multiple K squared. But as we have the upper bound of K fixed, the runtime complexity is O the number of V over 4. So we can get it. Okay, let's look at the second question. There are 5 small questions, and the requirement for this question is that use the restricted method to prove the NP complexity of the following problem. The first question is that for a weight graph G equals to V E W, with W like this, E head to Z, and integer W. Determine whether G contains a circle whose total weight is at most W. The answer is that if we set each edge weight as -1 and W as n, we can get the Hamiltonian circle, and it is, of course, NP completed. And for the second question like this, determine whether a graph G contains no smaller than K vertex V plus, such that for any two vertex UV belongs to V plus, the distance dg UV is no smaller than smaller d. The question is that if we set each edge weight is A and D as 1, we can get the clique. So it is NP complete. The third question is determine whether a graph G contains K vertex V plus adjacent to at least L vertex outside V plus. If we set K equals to n minus 1, get the dominated set. So we can get the conclusion that it is NP hard. And the fourth question is determine whether a graph G contains larger than K vertex whose delineation results in at least L component. The answer is that if we set L equals to the number of V minus K, then we get the vertex cover. By setting L equals to the number of V minus K, we are asking whether there is a vertex set of V plus of size K, such that the deletion of These vertices destroy the old edge in G, resulting in L isolated vertex. That is, whether G contains a vertex cover of size K. Okay, let's look at the last question. Question is that determine whether it is possible to choose some objects from a collection of n rectangular solid objects of dimension Li by Wi by Hi, where I belongs to 1 to n, and put them into a box of dimension L by W by H without leaving any space. Set the answer is that set C to be a collection of n rectangular solid objects of dimension Li by 1 by 1, and the dimension of the box to be L by 1 by 1. Then we get the subset sum. By the restriction, we are asking whether there is a sub collection of rectangles such that their lengths sum to L. Therefore, the problem contains subset sum as a special case. Okay, let's look at the third question. Prove that it is NP-complete to determine whether a graph G equals to the group V and E contains a complete subgraph with low smaller than number of V over 3 vertices. The answer is like this. Let L equals to G equals to VE. G contains a completed subgraph with low smaller than the number of V over 3 vertices, and L is in NP. That because there exists a polynomial vertification algorithm V for L. V runs in all the number of V plus squared and E. And the solution is like this. This is the pseudocode. On input G equals to VE, V plus. If V plus is smaller than V over 3, then return false. For smaller V plus in big V plus do. If smaller V plus don't equals to big V, then return false. If the number of big V plus is no larger than 1, then return true. For U in V big V plus do for V in the big V plus minus the group of U do. If the UV don't belong to E, then returns false, and finally returns true. And we can reduce, so we can say that L is NP hard, and then we can reduce the NP hard problem silic to L. The following algorithm R gives a polynomial time reduction for silic to L. First, on input G equals to VE, K, V plus equals to V, E plus equals to E. If K equals to V, the number of V over 3, then returns G plus equals to V plus E plus. Else, if K larger than V plus over 3, then P is given by 3 times K minus the number of V. Add P new vertices U1, U2, UP to the big V path, and then return the group. Else, if K is smaller than the number of V over 3, then PQ is given by compute the number of vertices to add the number of V, K. Well, the P is number of the new vertices that will be part of the completed subgraph of size, the number of V plus over 3, and number of the new vertices that will not be part of the completed subgraph. And then we can add p as a new vertex x1, x2, xp to the big V class. And for each vertex xi, do the following things. For every vertex v, a small v plus belongs to big V plus, if xi is now equals to v small v plus, then add edge xi v plus to e plus, and the q new vertex y1, y2, yq, and returns the g plus equals to v plus e plus, and compute the number of vertices to add nk. N plus is given by n, k plus is given by k. We repeat the following until we return the following is like this. If 3k plus 3 equals to n plus, then returns to k plus minus k dot n plus minus n minus the difference between the k plus and k. If 3k plus is smaller than n plus, then k plus is given by k plus multiple and 1, and so as to n plus. If 3k plus is larger than n plus, then n plus is added by 1. And note that complete number vertices to add runs in polynomial time. It is because for any n, in the worst cases k equals to 0, n plus will be at most 3 over 2n, so it runs in on, and the return file p and q will be n on. Thus, a runs in on squared time. We now show that in each of the 3 cases, k equals to v, the number of v over 3, and second is k larger than v over 3, and the third one is k smaller than v over 3. If and the group, the pair gk belongs to clique if and only if the group of g plus equals to L. The first one is that if G, the pair of GK belongs to clique, then there exists S belongs to V of size K equals to V, the number of V over 3, and S is clique. So the group of G plus is equals to G belongs to L. And if it's not equals to clique, then the size of the largest clique is smaller than k equals to the number of v over 3. So it's not belongs to L. And the second situation is like this. If gk belongs to clique, then there exists S belongs to V of size k and S is clique. After adding p equals to 3k minus v with number, isolated vertex, the total number of the vertex in V plus is 3k. Therefore, the group of G plus belongs to L. And on the other hand, the situation is just the other side. And the third situation is like this. If GQ belongs to EQ, clique, then there exists 3S belongs to V of size K, and S is the clique. After adding the size X of P vertex, each of which connected to all other vertices in V plus. S or X will index a complete subgraph of size K multiple K at P in the group of big V plus big E plus. After adding the Q isolated vertices, the number of big V plus equals to big V plus equals to the number of big V at P at Q equals to 3 small k plus, and equals to 3 times the sum of k and p. Therefore, the group of G plus equals to L. And on the other hand, it's also similar proof. Okay, let's look at the fourth question. Prove that it is NP completed to determine whether one can delete almost k vertices from a graph to destroy all 4 circles. Let the solution is as this. Let L equals to G equals to V. One can delete lower than k vertices from G to destroy all 4 circles. So we need to determine that L is in NP. The following describes polynomial time vertex graph for L, giving a certain set of vertex phi plus of size larger than k. Run BFS starting from every vertex on the indexed subgraph GV minus V plus and check if there is a full circle. If there is a full circle, return false, otherwise return true. And L is NP hard. We can reduce the NP hard problem vertex cover to L by following a full circle for every edge in the graph. The following pseudocode describes a polynomial time reduction from vertex cover to L. Well, on input G equals to VEK, G plus given by G. For every edge, EI equals to UV belongs to E. Do the following. Add 2 new vertices xi, yi to G big G plus and add 3 edge U xi, xi, yi, v to G plus and k given by k returns to the group of big G plus and k plus. We now prove that GK, the group of GK belongs to vertex cover if and only if G plus K plus equals to belongs to L. Well, assume there exists a vertex cover VC of size larger than K in G. Deletion of the vertex in VC from big G plus will destroy all 4 circles that are originally processed in G, as well as all new first circles formed during the reduction. Therefore, the group of big G plus K plus belongs to L. Assume there is no vertex cover of size larger than K in G. This means no vertex set of size larger than K can be deleted from big G plus to destroy all 4 circles. Therefore, the group of big G plus K plus don't belong to L. Okay, let's look at the fifth question. Prove that it is NP completed to determine whether a can delete almost k vertices from the group to obtain a bipartite graph. There is a hint. Hint is a graph is a bipartite if and only if it contains no odd circle. So it's like that. Let L equals to G equals to VE. One can delete larger than k vertices from G to obtain a bipartite graph. L is in NP. Similar with the fourth question, and let's look at the details like this. A polynomial time for this function for L exists. Given a statistical significant set of vertices V plus of size larger than L, run BFS starting from every vertex on the index subset, and detector, the key point is that the detector if there is an odd circle by making vertices in alternating layer with 0 or 1. If there is an odd circle, return false, then return true. First, L is NP hard. We can reduce the NP hard problem vertex covered by following a 3 circle for every edge in the graph. And the following should do to drive a such a problem. And let me check. Okay, that's right. And then the pseudocode is like this, similar with the first solution. So first question solution, and on input g equals to vek, the g plus is given by g. For every h, ei equals to uv belongs to e. Do the add a new vertex xi to g plus add a 2h uxi vxi to g plus and k plus given by k returns to the group of g plus k plus. We now prove that the gk belongs to vertex cover if and only if the g plus k plus belongs to L. If gk belongs to vertex cover, there exists a vertex cover Vc of size of k in G. Deletion from G class will destroy all the circles original presented in G and all new odd circles introduced during the construction of G class can obtain a bipartite graph. Therefore, G plus of K plus belongs to L. If GK don't belongs to vertex cover, there is no vertex cover of a size belongs to no larger than K in G. This means no vertex of size no larger than K can be deleted from G plus to destroy all the ordered circles. It means can obtain a bipartite graph. Therefore, the solution is the proof is done. And the second last question is use a reduction from 4 sets to prove that it is NP completed to determine whether a graph G equals to VE contains a connected vertex cover of the size almost K, i.e. a K vertex cover V plus with G plus connected. Hence, we make the reduction from reduction from 3 sets to vertex cover by make some changes to satisfaction testing components and adding some extra vertices at the edge. Well, the solution is like this. Let L equals to G equals to V E. G contains a connected vertex cover of the size almost K. L is in NP. The following pseudo derive a polynomial time vertex for verifier V for L. V is like this. On input, if the number of V plus is larger than K, then return false. And if there exists the V plus belongs to V plus such that V plus don't V plus, then returns false. And if there exists the UV belongs to E such that neither V or V is in V plus, then returns false. And run DFS from any vertex V plus belongs to V plus in the index graph G V plus, and then return false if any vertex in V plus is not exists, and finally return truth. And now we know that L is NP hard. We can reduce the NP hard problem for set to L. The following algorithm R gives a polynomial time reduction from full set to L. And for each variable ui belongs to L or belongs to U, construction an hui hat to form a truth setting component Ti. For each class Li, L1j, L2j, L3j, L4j belongs to C, construct a complete component K4 on four literal vertices L1j, L2j, L3j, L4j to form a satisfaction testing component Sj. For each consistency pair Sj and Sj plus 1, we add a vertex Wj, and for each I equals to 1, 2, 3, 4 group, add each Wj, Lij, and Wj, Lij plus 1. For every iterate vertex L in each Sj, if L equals to Ui, then add an edge between L in Sj and the vertex Ui in Ti. And if L equals to Ui hat, then add an edge between L and the vertex Ui hat in Ti. And K is given by this. G is the graph formed by the above procedure. And then return the group of G and K. Now, we show that UC from the group belongs to 4SAT if and only if the group of GK belongs to L. And the fact is that for any collective vertex cover P plus of G, P plus must include at least one vertex in each Ti, at least the three vertices inside Sj. So, phi hat is larger than U multiple 3 times C. If UC belongs to 4 sets, there exists a true assignment phi that satisfies C. If Ui is true in phi, put the vertex Ui into vertex cover V plus. Else, put the vertex Ui hat into big V phi, big V plus, big V plus. And for each Si, one of is for literals is true, and we put the other three vertices into V plus. We then put all Wj into V plus to get a vertex cover of size K equals to U multiple 4 C multiple minimum 1 minus 1. Therefore, the group of GK equals to L. And if on the other hand, if GK group belongs to L, there exists a collector vertex V star of size animals K. It follows the fact that V star includes exactly one vertex in each Ti, exactly three vertices in each Sj, and all Wj. If any Wj is not connected, then we have to include two vertices instead. The remaining ones from Sj and Sj plus 1, the vertex will exist U multiple 4 times C minus 1. We can obtain a true assignment phi plus there, phi star satisfying C by stating Ui equals to 1 if and only if vertex Ui belongs to V star. Therefore, the group of VC belongs to 4 SAT. Okay, look at the second, the last question. The question is that the self-reduction, suppose that SW is a polynomial type algorithm for subset sum, i.e., determine whether a set of S of positive integers contains a subset that sum W. Use ASW as a absolute subroot to design a polynomial time algorithm to find a subset S from S, subset S plus from S, whose the sum equals to W. Then, when such an S exists, Okay, solution like that, we can design the algorithm as follows. If a SW equals to true, so for every SI in S, if a SW equals to true and a S multiple SIW equals to false, then S is given by S minus SI, S plus equals to S plus SI, and W is given by W minus SI as values. If W is equals to 0, returns SI, and else returns minus 1. So here is an explanation. For this algorithm, we check the element Si in S one by one. If A SW is equals to true, and A S minus SI W equals to false, which means that Si is necessary for the subset, then we can remove S from S, Si from S, and let W minus the value of Si. Then we can resume the solution until W equals to 0, which means that we have found all the elements in the subset. For the time consuming, we just run O(n) times, so ASW runs, which is a polynomial time. Thus, we know that the time complexity is polynomial. Okay, this is the end of the presentation. Do you have any questions?